back, everyone. So I'm going to So the today's lecture will be about some sort of soft results concerning the interaction of chromatic homotopy theory and algebraic K theory. And by soft, I mean things that, well, two things. One is that you don't really need to do any computations to prove them. And they don't tell you what something really is. They maybe tell you that one thing is the same as another thing, or that something vanishes, or stuff like that. But they're also very generally valid. So there'd be sort of more or less three such results: purity, soft redshift, and descent. But first I'm going to start with a small recap from last time. So recall that, so to speak, spec of the p-localized sphere spectrum is a chain of points indexed by height, which is non-negative integer. And there's two candidates for what you could call the complete local ring. At height and point. One is this object called the Tn local sphere, which is, so I guess maybe like you take sphere, and then we have this sequence of elements, inductively defined sequence of elements p, v1, and so on. And when you mod out sequentially by each of the previous ones, then the next one becomes defined, and at Vn you invert it. You invert a Vn, and then you pass to the inverse limit. So this is maybe the most fundamental choice of so it's closest to the sphere spectrum. But it's very hard to calculate. Say, hard to calculate the homotopy groups. In principle, you'd kind of need to understand the homotopy groups of spheres to get started trying to understand the homotopy groups of this guy. But there's another choice, which is apparently of a different nature. So that's En, that's the Moravia theory. So this is more specifically, we had this Moravia theory functor, which takes as input a perfect FP algebra together with a formal group over that perfect FP algebra, and we can take FP to the n in the Honda formal group, and that'll be sort of the official definition of this Moravia theory. And this one is closely tied to algebra, as opposed to topology, which is kind of what we're seeing here. So the algebra of formal groups, more specifically. It's literally a functor, which takes as input formal group data. And the homotopy is very simple. So En is even periodic. And the pi 0 En is kind of non-canonically Witt vectors on Fp to the n, and then you have just as many formal parameters as you have here. Well, p is a formal parameter in the Witt vectors, and then you have maybe some u1 up to un minus 1. And the formal group that you have over this, for this guy, so which lives over this pi naught ring, is the universal deformation of Hn. And maybe I'll add another thing that I kind of forgot to mention last time, but this is even periodic, so recall that that means that the odd homotopy groups vanish, and the even homotopy groups are just the tensor powers of pi 2, which is locally free of rank 1. And what is pi 2? It's actually just the cotangent space for this Quillen-formal group. And then, well, yeah, we also have so here in En we have the Hasse invariance, the Quillen-formal group has Hasse invariance. So Vn will be in, because of this, pi 2 p to the n minus 1 e mod p v1 up to vn minus 1. Pi minus 2, yeah, minus 2 maybe, yeah. Oh, I hope maybe I messed something up there. And up to this notion of equivalence that we discussed when talking about self-maps in the previous lecture, these are the base change of the p v1 vn living over the sphere spectrum. So that's kind of actually more or less how you define the notion of a Vn self-map, by this compatibility with Hasse invariance when you have an even periodic cohomology theory. Okay. So yeah, we have this one thing which is kind of algebraic and in principle easy to understand. That's Morava-E theory. And then we have this more complicated thing, which is maybe what we're in principle more interested in because it's closer to the sphere spectrum. And the big question is, how far apart are they? Well, there's certainly a map. So we have LTN sphere. So En is Tn local because sort of by definition P up to Vn minus 1 complete and Vn minus 1 acts invertibly because this was height n formal group. And there we had this telescope conjecture. That if
you consider the map itself as a sense 1 to 1 in pi 0.
Exactly, yeah. So it's a ring, so it has a map from the unit, the sphere spectrum. That's the unit map, yeah. Yeah. So the telescope conjecture says that if X is a Tn local spectrum, and if X tensor En mod P V1 Vn minus 1, so this is called Kn, Morava-K theory. If this is equal to 0, then X must be equal to 0.
Okay, so the definition of the tensor over what?
Over the sphere spectrum. Yeah, I mean, it's the tensor product in spectra, so smash product.
Okay, and again, I forgot now, the definition of LTN SP means?
Oh, this is just the essential image of this functor. So there's a this LTN functor was, well, it's the same, it's this, but with a, you'd put an X. I mean, it's this operation.
Ah, okay.
Yeah.
So all the things which are kind of complete, completion, which are of this type.
Yes, exactly.
That they are complete relative to the previous ones, and Vn is invalid.
Yeah. Okay. That's the telescope conjecture. Okay, so, but whether or not it's true, and now we know exactly when it's true and when it's not, like for which n, it's in P it's true, but whether or not it's true,
once you tensor with En, you get something which is like a module over En.
Yes.
And those are classified easily like as modules of...
Oh yes, especially modules over Kn. I mean, so Kn is kind of like the residue field.
Yes.
Yeah. And indeed, the theory of modules over this ring spectrum is incredibly simple. It works basically just like the usual derived category of a field. everything is a direct sum of shifts of Kn, every Kn module. And that just follows pretty easily from the fact that the homotopy groups of this, like pi 0 is a field, and then you have some periodicity.
Okay, and if something is has a Kn module structure, but you don't give the module structure, can it have different Kn module structures? Or?
Well, it's actually even worse. I mean, there's not the algebra structure on Kn is not unique. So there's some choice in making these quotients into algebras.
Because you're not doing the infinity, but
yeah. In fact, there is no E infinity. There is no E infinity algebra structure on Kn. There is an E1 algebra structure, but in fact, there's many E1 algebra structures. But never mind. Never mind.
This is because you didn't use the infinite, because you're working modulo.
Yeah, because this just means taking a cofiber. So it's not like.
Is it analogous to the problem of like in Moore spaces to define product of monopole?
Exactly.
About n, and then with 2, it's even worse. Like
Yes.
When p is 2,
it's not. Yeah, when p equals 2, you're right. Even this guy, when p equals 2, it's not even like associative, or not even commutative, not even homotopy commutative. Sorry, it is associative, homotopy associative. It's not even homotopy commutative. But these issues are not really issues, so they're just annoying. All right. So whether or not it's true, we can study a replacement of LTN, which kind of forces the conjecture to be true. And this is the LKN. So let me give the definition. So a spectrum is called Kn local if there's no homotopy classes of maps to X from any X which is killed by Kn. And then we have, then we have the Kn localization, which is the initial map to a Kn local spectrum. And let me make a remark. One can view this Tn localization, I mean, I sort of gave a formula for it, but one can also view it in a similar way. So X in the spectra is Tn local if and only if there are no homotopy classes of maps from Z whenever Z tensor Tn equals 0. Where Tn is the sphere mod P V1 Vn minus 1, and then invert Vn. And this condition is independent of the choice of the self maps. So it's kind of.
Or you can do both with powers.
Yeah.
Because whenever you choose them in a reasonable way, it's the same.
Yeah, they always generate the same fixed subcategory. Any choices you make of the self maps, the resulting TNs, they generate the same fixed subcategory. Okay, so right. So the completely parallel story, and this is more generally, you can do this with any spectrum replacing Tn or Kn, and this is the formalism of Bausfield localization. Okay, and the telescope conjecture can be reformulated as saying, well, there's a natural map from Tn localization to Kn localization. In other words, if this condition is satisfied, then this condition is satisfied. And the telescope conjecture is the question of whether this map is an isomorphism. So whether these two localization functors agree. And this is actually the better way to look at it, because strangely enough, it's kind of much easier to produce. Well, I'll say a few words. Right. So, but first I want to say, so I kind of gave a formula for Tn localization, even though it's not really something you can calculate with in general. But now I want to say how you can understand the Kn localization. So
the construction of this initial object, is it like some general nonsense under some condition there is?
yeah.
Okay, it's not...
Yeah, I mean, basically what you want to do is you want to take all of the, given your x and you want to construct, say, this guy, yes. You take all of the z satisfying this condition equipped with a map to x, and you take the colimit over that diagram. And then you take the cone of that, and that will describe this guy.
You don't have to repeat this.
No. But the only trick is to make sure the set theory works out. Yeah. But
I'm not sure about because like when you take the colimit, you have some maps, but you can have the zero map, which is like taking your thing direct sum with Z.
Yeah.
Somehow when you take this thing, I have a feeling that somehow take direct sum with a lot of stuff which you don't need. So
no, but it works, and one knows a posteriori that it has to work, because this diagram will have a terminal object, which is the fiber of the map from x to its Tn localization. I mean, so the colimit does exist, and it does do the correct thing, like at least a posteriori. But yeah, I mean, so yeah, Bousfield's paper is very nice, so I can recommend it. It also gives lots of examples of Bousfield localization and how to compute with it. So yeah, yeah, I think so. It's like localization. It's a really nice paper of spectra with respect to homology theories, I think is what it's called.
But now you use a different language, because presumably when you take the limit, you are doing it like in the sum infinity.
Yeah. No, yeah, it's true. So, I mean, there's also, I mean, you can also look in Lurie, wherever Lurie discusses accessible localizations, you can also look in there and see versions of all of these results. Okay, so how to understand Kn localization? Well, so En was, again, this E theory based on Fp to the n and the Honda formal group. And we had this Morava stabilizer group from last time, Gn, which is actually, I defined it as a semi-direct product. But it's actually just the automorphism groups of this pair, consisting of this perfect Fp algebra and the formal group acting on it. And the idea is that the profinite group, this profinite group, Gn, acts continuously on En, where continuous with respect to the P V1 Vn-1 adic topology. And in some sense, this should be true by functoriality, but it's not literally what you get by functoriality is just that the discrete group underlying Gn acts on this ring spectrum.
What was Gn from last time?
It's a semi-direct product of Galois group of Fp to the n over Fp, acting on this ring of integers in some division algebra over Qp. Right. So that's the idea. But one can make it precise as follows. So there's a small lemma. So well, let me recall this general E-theory functor. So let me write perf FP for a category of affine perfect schemes over spec FP. And then let me say, so this is the stack of formal groups of height n. So then we have this slice category, which is a perfect scheme, perfect FP scheme equipped with a formal group of height n. And then E-theory, since I passed from rings to schemes, I should take an op. And then I get something, a commutative ring spectrum out of it. So that's Lurie's construction. So there's a small lemma. FGN, yeah, if we fix the height. Yeah, height n. So maybe I'll height equals n. So small lemma, so E is a sheaf, in fact a hypersheaf, say for the pro-étale topology. I mean, you have I mean, you can formulate stronger results, but this is all we care about.
Is it? Sorry. I wanted to ask if this lemma is due to Lurie, that you're going to give a proof.
Yeah, I mean, it's like a one-line proof. Yeah. Well, the reason is that if you look at the homotopy groups of E, let's say of R, comma G, so perfect algebra formal group, these are just sorry. Well, E is first of all it's complete, so it's the inverse limit of modding out by powers of p through Vn minus 1. So to check something, so to check sheaf property, we can check it by after modding out by p through Vn minus 1. And then if you take the homotopy groups of this, basically by definition, you just get like direct sum over I and z of omega tensor Ri, and that in degree 2i. So each homotopy group is is a quasi-coherent sheaf. So then, basically by the derived version of, say, faithfully flat descent, you get the sheaf property for each homotopy group considered as a spectrum, like sitting in degree 0 or sitting in degree 2i. And then by just going up the Postnikov tower, you deduce that this guy is a sheaf as well.
Can you remind me how you define the completeness of the, you said this E thing is complete.
Yeah.
And what was the definition of completeness?
Completeness was, well, when I gave the definition of Morava E-theory, I asked the pi 0 be complete with respect to the Hasse invariance, p up to Vn minus 1. But then it's also even periodic, and the pi, so it's and then because of this compatibility between the Hasse invariance and the p Vn minus 1 coming from the sphere spectrum, it's the same as saying that like that it's complete in the in the similar sense to this. Yeah, so it's complete also. It's so that I mean it would be enough to use the Hasse invariance for this argument actually, but in fact it's a notion of completeness that makes sense over the sphere spectrum. Okay. But on the other hand, Recall that this moduli stack of formal groups is just a quotient. So there's basically only one formal group, the Honda formal group. It's this quotient here. So we can then just map that, say, by pi. Oh, maybe I shouldn't use pi because of homotopy groups. F to point mod Gn. So then taking push forward. Oh no, I called it F. Gives a Pro-Étale sheaf.
To a point means to like spec FP?
Yeah, point, let's say spec FP, yeah. Or you could think of a map of topoi to like, well, there's a site of profinite sets equipped with a Gn action. Yeah. It's equivalent, it doesn't matter. Yeah. A Pro-Étale sheaf on point mod Gn. And in particular, we get an Étale sheaf, yeah, on the site of, in fact, hypersheaf. Again, hypersheaf on the site of finite sets with continuous Gn action. So if you just evaluate, so if you have a finite set T with a Gn action, then you can form T mod Gn, and that you can just restrict your sheaf to objects of this form, and then you'll get a so call this guy. I'll call it ENDH. So it was originally produced by Devenitz-Hopkins. Not by this method, but it's the same object. Then we have the following properties. First of all, so one way of talking about like an action of a profinite group on an object, at least an object if you consider it with some sort of discrete topology, is indeed giving a sheaf on this site of finite Gn sets. So we can consider this ENDH as giving some kind of spectrum, ring spectrum with a continuous action of Gn. So let's say that E is the map of sites. So point to point mod Gn. So it corresponds to the forgetful functor from finite Gn sets to just finite sets. Then if you take the pullback of this, which can be thought of as the underlying spectrum of this ENDH, well, you don't quite get En, actually. You have to complete. So, but once you complete, you get En. So this was supposed to be acting continuously with respect to this PV1 up to Vn minus 1 adic topology. So if you mod out by some power of P V1 up to Vn minus 1, then it's acting on something discrete. So it should correspond to some sheaf here. And then you can certainly take the inverse limit there, and you still get a sheaf. But the stock is not exactly going to be that. You'll have to recomplete to get this. Okay, but that's kind of a way of saying the underlying object is En. And the second property is that if you evaluate on the base point now, so so to speak, if you take the fixed points for Gn acting on En, so you evaluate on the trivial finite, the terminal finite set with a Gn action, then you get the Kn local sphere. And then there's another Galois property. So So let's say n. So if you have an open normal subgroup, and then by this I just mean the evaluation of this guy on like G mod n. This is a p vn up to vn minus 1 complete Galois extension with the group G mod n. And this is a Galois extension in the sense of Rognes. So I'll explain what that means.
G mod n, which acts on the target.
Okay. So what this Galois property means, well, first of all, something that follows just from it being a sheaf is that this is the fixed points of the. So that's one property, but the second property is the kind of the Galois property. That if you take this and you tensor in the completed sense, so you apply this completion functor after tensoring with itself, then this is the same thing as, how did I write it? Yeah, say maps from, basically maps from this finite set into En. So when you have a Galois extension of commutative rings like A to B, then when you form B tensor AB, that just becomes a product of copies of B. And it's the same story here. So. And there's a natural map just coming from the action.
So is it implicit that somehow there is a ring structure? Or?
Yes, there's a ring structure. Here was the target for my sheaves.
Ah, okay. So it's
Yeah.
ring infinity.
Yes.
Okay.
Yes.
So all of those are infinity.
Yes, that's right.
And S G mod n means the.
Oh, just the free spectrum on this finite set.
So is it like taking the finite set plus and taking the suspension?
Yeah. So I was saying this whole thing is this. This guy is just, say, a direct sum of copies of S indexed by G mod n. Yeah. Right, so actually, just from 1 and 2, so let me make a remark here. 1 plus 2, and plus, this is crucial, the hypercompleteness. Gives a spectral sequence. So just to give an indication of what this is saying, if you do the continuous, you take the continuous cohomology of this Morava stabilizer group acting on the homotopy groups of En, then there's a spectral sequence where this converges to the homotopy groups in degrees pi minus q of the Kn local sphere. So this is a reasonable method for coming to terms with what this object is. This is known. So then what remains to be understood is what is the action of this group on that? That's kind of complicated. And then how to calculate the cohomology. And then this is a compact p-adic Lie group, so the cohomology is actually kind of manageable. So really the trick is trying to understand the action. But that's sort of a purely algebraic problem. Okay, so how can we interpret this let me sum up. So upshot. So we have LTNS, we have LKNS, and this is what the telescope conjecture is about. Yeah, actually, so I said the telescope conjecture was the claim that these two functors are the same, but in fact, it's also, if they're different, you have to see that difference already on the sphere spectrum. So, and then this is like an infinite Galois extension. So this is the bottom of a tower of Galois extensions, which ends in this Morava E-theory spectrum. And that's kind of the picture, the general picture of the relationship between this notion of complete local ring and this notion of complete local ring. Any questions about that?
So is it easy to see that it's enough to check just the sphere spectrum?
It's not so hard. So there's actually a, well, it has to do with the finiteness properties of this group acting. So it turns out that this, as a Tn local spectrum, this one is idempotent. So once you're in the Tn local world, Kn localizing is just the same as tensoring with this guy.
Inside Tn local.
Yeah. Yeah.
And the GN extension is like a limit of the, no, ENN. You say that, what is the relation between EN and the co-limit of the?
Yeah, that's this. They're the same up to this completion.
Okay,
so this is like the co-limit over N of EN N.
And is it the case that LKNS is like the fixed point of N on capital?
Yes, that's true. Yep, I wrote that up there.
And how do you define it when N, capital N is just is a profile group? Yes, capital N is.
Capital N I chose as an open normal subgroup of this profinite group here.
No. I asked you about GN then. But GN is profinite. I would define the homotopy, the fixed point for a profinite group actually.
No, I define it as the existence of this guy here with these properties. I define that as the existence of a sheaf on this site, such that the underlying object is this guy up to completion, and the,
okay, so it's not a construction.
This is an interpretation here. When I write this, it's an interpretation of the thing which formally is this. Yeah. This is definition, say.
Is a definition.
Yeah.
That is you. So you said you have a good theory if you have this kind of sheaf, and then you say that those are like the homotopy fixed point of capital N, but you have a problem to define directly because of the continuity issue.
Yes.
And so you avoid it by saying that you have this.
Exactly. So this was the solution basically of Devnitz-Hopkins to this issue of making this precise. Of course, with this pro-étale or cadence stuff, you can kind of directly make sense of this, but we're not going to, that direction will not be so useful for us, so we won't discuss it. Other questions? Okay, let me make a remark. I realize I haven't gotten to algebraic K-theory yet. I had to... maybe I should do an example, actually. Let's do an example. So n equals 1. Okay. So then recall that E1 is just the p completion of the complex K-theory spectrum. Gn here is just Zp cross. So let's, and then we have some torsion subgroup, which is finite. And then we have, say, Zp cross mod mu identifies with Zp. Then the result is that the K1 local sphere, so then we can choose the generator. So we have.
Yeah, you need to choose a generator which you can. Yeah. Is not.
No, but there's kind of a canonical choice because you can. So you can
like either 5 equals 2 or 1 plus p.
1 over 2p log x to the p minus 1 implements this isomorphism. So you can choose a canonical generator. This is, yeah. Well, anyway, you can choose a G in any case. So then this is a finite group, so we do know what it means for that to act on that just completely naively. And so we can form the fixed points like mu. And then we have to further equalize this action of 1 minus g on that guy. And then we get a fiber sequence like this. And at odd primes, this mu has order prime to p, so that this fixed point is just happening at the level of homotopy groups. At the prime p equals 2, this is just a z mod 2, and it's actually the equivalent to passing from ku to ko. So as you can see in this case, because of the very simple structure of this group, it's really simple to understand this guy in terms of this guy, which is completely known. So in particular, you can easily calculate all the homotopy groups of the K1 local sphere. Okay.
Also, is it true that the Zp cross-section on Ku is related to Adams operation?
It's the same as Adams operations, yeah. So this Zp cross-action, so yeah, the way you can normalize it is like if you have, say if you have G and Zp cross, it acts on pi 2 of Ku by multiplication by G. And then there's an action on the level of ring spectra, so that tells you what it is on every homotopy group. And it also forces it to be the same as the Adams operations. Okay, so let me make a remark.
So that the Adams operations are not completely stable. No, okay, in this case, when you do prime to p.
Exactly, exactly.
But otherwise you get some, okay.
Correct, correct. Yes. Okay, so let me make a remark. So the hypercompleteness here is crucial. Is kind of at the heart of the matter. So there's a theorem recent theorem, not yet written, says that in some sense you can lift this hypersheaf, you can lift this sheaf to the Tn local world, but only as a sheaf and not as a hypersheaf. So there exists a unique sheaf of Tn local objects in C-alg spectra. Again, on the site of finite Gn sets, such that, so one is that, let me call it like a pre, or maybe I'll say Tn, maybe Etn. Okay, just making up notation on the fly. But if we do Etn or maybe ENF. Yeah, that matches. Sorry, I'm just thinking that matches the what we had with localization functors earlier. So if you take ENF of a point, you get the Tn local sphere. The second thing is that if you Kn localize this ENF, you get En. And this is even section-wise.
Section.
Without sheafification, exactly. Yeah. En, I should, DH. Yeah, that was my notation. And the third is that you have the same Galois property. And furthermore, we also have that if you take E upper star of this guy and then complete it, you still get the usual En. The underlying, well, so you have to be careful about this intuition of underlying spectrum when you're not working with hypersheaves. And in fact, this En Devenitz-Hopkins is exactly the hypercompletion of this this finitary version, this Tn local version. So you could read this as somehow saying that Kn localization is the same as hypercompletion. So this somewhat technical distinction between a sheaf and a hypersheaf is actually at the heart of the matter in this theory of chromatic homotopy theory. And in fact, so spoiler alert, so when n equals 2, the counterexample to the telescope conjecture comes as follows. So it comes by combining two facts. One is that if you take the K2 local K theory, then you get hyperdescent. Along this tower from the K1 local sphere to E1. So, and that is a theorem of Ben Moshe, Carmeli.
What is K? K?
Just a sec. Schlank, Janowski. What is K? Algebraic K theory.
Algebraic K theory, but how you evaluate it
on a ring spectrum? I'll tell you in a sec. Yeah. Okay. And then second, so LT2K satisfies descent. That's yeah. Clausen, Matthew, Naumann, Noel. This is not really the relevant part, but I'll just for, but not hyperdescent. This is the relevant part. And that is these people who disproved the telescope conjecture. Let me hope I wrote it again. Okay, Burklund-Hahn-Levy-Schlank. So the way they show that these two functors are different is by showing that they have different kind of formal properties. One satisfies hyperdescent and the other one doesn't. They don't explicitly, they don't necessarily, well they do, they spell it out, but what the argument doesn't, in its most basic form, the argument proves this. It doesn't explicitly produce a spectrum where the K2 localization is different from the T2 localization. You can figure out how to do that from their argument very easily, but that's not what they're explicitly doing in the argument. In the argument, they're explicitly doing this.
The same is true for every n?
Same is true for every n. It's a very similar story for every n. Yeah, although, I mean, but be careful. I mean, it's only a, well, it depends what you mean. Let me say it's very similar for every n. There's a, okay, so maybe I should say, so. The second statement, yeah, the second statement is true for every n. So actually this is it would be maybe a major open problem. The LKn plus 1k satisfies hyperdescent. For LKn sphere going to En. That's one of the main open problems in this circle of ideas. Their work gives it for a certain sub-extension of this, but not for the full thing. And that sub-extension happens to be the same as the full thing at height 1, but otherwise not.
So here you wrote okay, the n is 2, and this, okay, you wrote Gn above. Okay, to explain.
Yeah. Okay. Now I want to, before the break, I want to do a little bit of philosophizing, kind of, which will set up the second half of the lecture. So in the end, so it's the K theory of the K1 local sphere gives the counterexample. To the height 2 telescope conjecture. Yes?
How, you said in the last lecture, like for n greater than or equal to 2, the telescope conjecture is known to fail.
Yes.
And but this is, so you said this is open.
Yeah, this is open for, well, yeah, wait, what's the problem?
So how do you imply that you get a counterexample?
Oh, sorry, well, sorry, this is open for n bigger than 1. It's not open when n equals 1. I just stated the theorem that says it's true when n equals 1.
When for n greater than 2, strictly greater than 2.
Oh yeah, no, yeah. These guys still identify a sub-extension of this where they have hyperdescent. Yeah, this is a big group, Gn. It has a normal subgroup, which is almost the whole thing. It has a quotient isomorphic to ZP cross. And then so there's a ZP cross tower you can put here. And they prove hyperdescent here, but hyperdescent here is not. Yeah.
Okay, and then the other one doesn't satisfy hyperdescent for this extension?
We don't know.
The other, I mean,
oh, the T2, yeah, T2, exactly. The Tn plus 1 local K theory does not satisfy hyperdescent here.
in particular is a way to...
Exactly. But that's not actually even how they do it. They actually switched from these Morava E theories to something called BPN, which is related but not the same. So it's not. Let me stick to this. Let me stick to just this situation here. Okay. So right. So why does algebraic K theory give a counterexample? Or why would it be promising to look at algebraic K theory? Counter example. So the answer is its chromatic behavior is backwards. Or upside down, maybe, I don't know. So let me explain what I mean by that. So usually, say for spectra showing up in algebraic topology, so for example, the sphere spectrum or any finite spectrum, you have some properties, for example, like understanding the Tn+1 localization is harder than understanding the Tn localization. And similarly for Kn+1 or Kn, when you increase the height, it gets harder to study. Height 0 is just rational stuff. I said at the beginning that's easy. It reduces to pure algebra. No problem. But when you get to height 1, it's a little more complicated. Height 2, it's even more complicated. You're going deeper and deeper and deeper into this chromatic story, so it stands to reason, right? And also, LTN, the telescopic thing, is harder than LKNX. That's also what I said. I mean, to understand this, you kind of have to understand these VN self-maps, and you have to start with something like the sphere spectrum. Whereas here, it's just enough to know Morava E theory and this profinite group acting on it, and then you can, in principle, get going. But for algebraic K-theory spectra, it's the opposite. This is quite remarkable. So LTN+1 easier than LTN, LKN, LKN+1. And even more shockingly, LTN is easier than LKN. So the rest of today's lecture and tomorrow's lecture will be about exploring this backwards behavior. Sorry, next Tuesday. About exploring this kind of backwards behavior. But let's take oh wait, any questions?
So you'll explain in which sense?
Yes. It's actually true in a very strong sense. So yeah, it's what I'll immediately start with after the break.
So in this theorem about existence of uniqueness, okay, the uniqueness, so you look at the, okay, since you have a lot of structures, certain things are all, you don't have a rigidity, but is it important to have the Galois property in the theorem?
I think it is, yes. Yeah, that helps with rigidify. Yeah.
Okay. So I forgot to write the Galois. It was.
I mean, what we really prove is that any Galois extension of Kn local rings. So if you have a if you have a Tn local ring and a Galois extension after Kn localization, then it lifts uniquely to a Tn local Galois extension. So it's kind of maybe morally similar to like this nil invariance of the étale site in algebraic geometry, but a little more sensitive.
Okay, Galois extension for finite group.
Yeah.
So the Galois extension in this sense of the Kn localization of some Tn local infinity guy. So this kind of lifts uniquely
Yeah.
to, okay. This is one fact in this story, okay.
Yeah, that's essentially, I mean, that's the real theorem. I mean, this is just a consequence.
I remember I've seen some paper, yeah, maybe it was,
Well, there's no paper yet for this.
Think about lifting of finite Galois, I think I saw it somewhere.
Oh yeah, so these guys, I'll get into this a bit later, but these guys lifted these ZP cross extensions. Explicitly lifted these ZP cross extensions, like this one, for example, to the telescopic world. Yeah, so maybe I should say when n equals 1 in this theorem, that was these guys that did it. Yeah, but this, yeah.
No, okay. So they lifted the ZP cross extension to the...
Yeah, so they proved this theorem when n equals 1, in other words. And also, when at higher n, they lifted a small part of this to the telescopic world, the Tn world.
Okay, but you say there is no hyper... okay, but for the finite Galois group...
Yes, exactly, yeah.
No, but I've seen some, I'm not really sure where, very vague, I mean, this theorem in convertive algebra, let us say, lifting of finite algebra or finite G tensors,
Yeah.
here you are doing it in algebraic topology, like in the world of infinity things. Of course, so I've seen somewhere, I mean, this kind of lifting of étale algebras in this context of infinity ring. This is
yeah, in certain contexts, it's, I mean, it's a, yeah. In certain contexts, it's of course known. But this is maybe a bit more surprised. I think people were surprised by this.
Someone defined maybe blue, someone defined...
Yes. Yeah. Then it's easier to prove such results. Yeah. I'm going to release everybody for the 5-minute break. We're going to start finally talking about algebraic K-theory. So let me start, let's say with a classical situation. So if R is just a ring, then let me say vect R is the category of finitely generated projective R modules. And then we can, only allow isomorphisms between them and we get a groupoid. And it's actually a groupoid. It has a direct sum operation, which makes it into a sort of a commutative monoid in groupoids. And then one definition of K-theory of R, maybe this is Siegel's definition, Graham-Siegel, is you take this groupoid under direct sum, and then you group complete it.
You mean the book with the classifying space? Or?
Well, this is a classifying space. I mean, this is like a disjoint union of classifying spaces of general linear groups.
Okay, no.
Oh, I see what you mean. Yeah. I'm sorry, I was implicitly viewing an infinity groupoid as like a groupoid as an infinity groupoid and thinking, yeah, I can do algebraic topology with it. Yeah, exactly. Yeah. Right. So what is this explicitly? It's some kind of, it's a spectrum with underlying space or anima. So you take, so let's call this M. So you can take like M cross M, and then you equalize an M action on it, where it's acting on maybe on the left here by the group operation, and on the right here by the group operation. So this is So implicitly, so this mapping to K-theory of R, this is like sending the class of some V and W to the virtual vector space, so to speak, V minus W. That's one way of realizing this. So you can take the same definition for any, say, connective ring spectrum. Let's say E1. So say finitely generated projective means it's a retract or a summand of a direct sum of copies of the unit module R to the D. So the only difference will be that it won't be a one groupoid anymore. It'll be maybe an infinity groupoid if the ring spectrum has higher homotopy groups, but the formalism still works just fine.
But for the objects, you just take that's okay.
Yeah.
Okay.
Yeah.
And of course, you can take left or right, finally generated projective. And
true. Yeah. So there's in principle two.
Between them, like they are home in this world, the dual makes sense.
Yes. Yes, it does. Because for these, it's because direct sum, finite direct sum is the same as finite product. And then it's a retract, so fine. And yeah, the two K theories will be canonically isomorphic. Like if you do it based on left modules or right modules. Because the categories, the groupoids will be opposite to each other, but that doesn't change the geometric realization.
Yeah, but when the ring is commutative, this gives an involution.
That's correct. That's correct. Yes. Yes. But let's just fix, I always mean left modules. Let's just fix a choice. Okay. So for non-connective, and actually in general, it's better to use for non-connective R. It's better to use perf R instead of vector. So this is the fixed subcategory of modules over the ring. So dr, which is just R modules in spectra, generated by R. So yeah, finitely generated projective means you're in the additive category generated by R plus retracts. And here you don't just allow additive operations, you also allow cones and shifts. So you kind of allow triangulated category operations and retracts again, and that's perf R. And then use a version of group completion, which also forces say like y equals x plus z whenever you have x to y to z, a cofiber sequence. So, or a distinguished triangle. Or really, you adjoin a homotopy between these two things, and then also higher coherences. And this is the, say, the S dot construction of Waldhausen, which does this, which is this version of group completion, which does this. And it's a theorem of Waldhausen. He was very, very careful and diligent and checked that it's the same thing. So for R connective, the K-theory based on the finitely generated projective modules is the same thing as the K-theory based on perfect complexes. So let's just say these are all just KR, and let's say that's always defined using perfect complexes. So on the level of K0, this is kind of classical. It's because and say R is if R is an ordinary ring and on the level of K0, and you're basically saying you can represent any perfect complex by a bounded complex of finitely generated projectives, and then to make an inverse to the natural map from the left to the right, you just send that complex to the alternating sum of the K-theory classes of the terms. So it's kind of, in some sense, going between dimension and Euler characteristic. Okay. Right. So now let me state some classical theorems. About algebraic K-theory. So R will be an ordinary ring. So I'm saying classical, so. So the first is a theorem of Mitchell, Steve Mitchell. So it's a spectrum. We can apply this whole telescopic chromatic machinery to it. And this says that when your height is bigger than 1, you get nothing. Lebowski. Right. Second theorem, Thomason, tells you what happens at height 1. Well, let's say that, spec R has finite Kroll dimension. And then the supremum over X in spec R of the virtual cohomological dimension of the Galois group of the residue field is less than infinity at the prime P. Very, very mild finiteness hypotheses. Then you get a formula for this T1 localization. And let's say R is over Z1 over P. Then you get a formula for this T1 localization. It's basically a tall cohomology, this T1 local K theory. So it's let's say R gamma, spec R, a tall. Well, I shouldn't use R, right? I'm pretending to be a homotopy theorist. Of some twisted form of a p-adic complex K theory. So it's a tall cohomology with some spectrum coefficients. I should go over to go over to another board.
It's like the étale K theory.
Yeah, it's going to be end up being the same as the étale K theory of Dwyer and Friedlander. But let me say it like this. Let me finish the statement and then so. Okay, so where is equal to, let's say, so we had this E1 guy, which was, again, also basically p-adic complex K theory. And then we have to hypercomplete.
You take chi.
Where the chi is sick. So this classifies the cyclotomic tower. The p cyclotomic tower.
You take the pullback of E1 is this
yeah, this sheaf on the side of finite ZP cross sets with stock p-adic complex K theory and with global sections, the K1 local sphere.
This is what you discussed before.
Yeah, it's Devenitz-Hopkins. Yeah.
Yeah, and then you have a notion of pullback of sheaves or pre-sheaves.
Yeah, so it's pullback in the sense of sheaves of spectra, but then I make sure to p-complete and hypercomplete. So what's the upshot of this is a spectral sequence. So HP, I shouldn't use P, right? Okay, HQ, spec R, étal. And then the homotopy groups of complex K theory by Bott periodicity and are just ZP in every even degree. But if you remember the ZP cross action and pull back like this under the cyclotomic tower, it exactly turns into a Tate twist. Let's say ZPI, and that's going to converge to pi 2i minus q of the T1 local K theory of R. So basically, T1 local K theory, or K1 local K theory, it's the same thing. Remember, the telescope conjecture is true at height 1, is just a tall cohomology with Tate twist coefficients, kind of wrapped up in a different way.
And Thomason used inverting the Bott element, but this is something...
That's basically V1, yeah. He even proved it was the same as V1 in an appendix, yeah.
He has more restrictive assumptions.
Yeah, so with the Keel-Matthew, we cleaned this up. Yeah, so we got this result, or in this form, maybe it's in the paper with Bargov. So in this form, C, Bott, Clausen, Matthew, remarks on K1 local K theory. Okay.
So in particular, if P equals 2 and you don't define cohomological dimension, then still this is kind of say converges in the right way.
Right.
This inverse limit
Yes.
of the...
Yeah.
Okay.
Yep. Right. So let me make say an addendum to this. So this is a theorem of, well, actually it's the same paper here. So I had this assumption that R was a Z1 over P algebra, which, if you want to be talking about a tall cohomology with Tate twist coefficients, it's reasonable, right? But actually it doesn't matter. So if you take any R and you T1 localize its K theory, it's the same as for R with P inverted. That's maybe one addendum. And the second addendum is that, well, let me say that there are two key aspects to Thomason's work. So maybe the first one is a tall hyperdescent. For T1 local K theory. And the hyper is again important for getting a spectral sequence like this. And the second aspect is the identification that LT1 K of R is p-adic K theory if R is strictly Henselian over Z1 over P, and that's Gabor-Suslin. So thanks, Ofer. Yeah.
Some question. So when you are working in this case of real number fields, where homological, because of the two, homological, so anyway, anything in K theory by construction is countable, and when you invert the both elements, you also get something countable.
Right.
When you have inverse limits,
Yeah.
you tend to get cardinality of the continuum,
Yeah.
so it doesn't fit with this kind of result, because when you have the spectral sequence, if you want something to be like the derived inverse limit of certain thing, and you have infinitely many contributing terms in the spectral sequence, or maybe not. I mean, I don't know which degrees are zero to consider, which PMQ you consider here, but for a given can you have infinitely many terms?
No. So this is one of the things you have to show. That in fact, the contributions from at the prime 2, you have contributions from like basically let's even say for Q, then you have the contributions which can all be traced back to R in some sense by a theorem of Tate. So, and you can check that this. So on the E2 page, you get infinitely many classes, and it seems like it's trouble. But when you go to the E3 page, all but finally many of them vanish, and that's the kind of thing you have to check.
On the E3 page.
Yeah.
On the E3 page, and this is also true for skips.
Right.
Over of this type.
Yeah.
This is okay, and so then you. Okay.
So it's the D3 differentials, or maybe it's the E4. Well, it's the differentials which in standard indexing are called D3 that kill things. So maybe it's the E4 page where you have the vanishing. Okay. But actually, one thing I might explain is that that's actually, it's not, it sounds like it might be hard to prove such a thing, but it's actually a general feature of chromatic homotopy theory called Tate vanishing. Maybe I'll explain, I'll probably talk about it. So that was the addendum. So there's maybe another, so there's a soft version. So LT1K has a tall descent for all R. Here, yeah, ordinary. Maybe here I should have said commutative, R commutative here. So if you don't care about hyperdescent and you don't care about, well, precisely identifying anything, then at least you have a tall descent. And in particular, Galois descent. And for that, you don't need any finiteness hypotheses. You don't need anything. And maybe that, yeah. Awesome.
Yes, for faithfully flat Étale algebras.
Yeah, faithfully flat, yes.
But
Yeah.
what about Pro-Étale and this kind?
No, for Pro-Étale, you'd need some kind of finiteness conditions. Yeah. Okay, and that was a big long comment on the second theorem, second classical theorem, and then the third classical theorem. And this is Grothendieck. So we've talked about heights 2 and bigger. We've talked about height 1. So what about height 0? Let's say that R is smooth over a field. Then if you take, so LT0, pi 0 of LT0, which is just the rational K theory of this, then that's a direct sum of Chow groups, rational Chow groups. So this is supposed to illustrate this idea that algebraic K-theory spectra are backwards. The higher height stuff is really easy. In fact, it's so easy it vanishes. Can't get much easier than the 0 group, right? The lowest height information is actually extremely complicated. We're never going to be able to figure out stuff about Chow groups of like a general smooth variety over a field. That's my opinion. I'm probably not alone in that assessment. Just two complicated phenomena are appearing there. The sweet spot is height 1. That's where it's not trivial, but it's still understandable. It's just étale cohomology, basically. And we can more or less understand étale cohomology in many situations. Okay? Okay, now let me state some higher chromatic generalizations. Okay, I'm going to start with actually a generalization of this result. So this is purity. So it's Marcus Lund, Leonard Meyer. Oh no, Matthew, yeah. Akil Matthew, Leonard Meyer, Georg Thoma. So now R is a ring spectrum. So it doesn't have to be commutative necessarily. So then LT n plus 1 k of R maps isomorphically to LT n plus 1 of Ln plus 1 F R. Don't ask me why I chose to write it with n plus 1 instead of n. Well, okay, maybe I'll tell you at the end why I'm writing it with n plus 1 instead of n. So this is for all n bigger than or equal to 1. So this does recover this result. So because if you take an ordinary commutative ring, then, so we're taking n equals 0, yeah? Then L1F, remember, it's built by piecing together the rationalization and the T1 localization. I should say, no, we take the convention, so that we take the convention that T0, so I was working in the P local context earlier, and then T0 is the same as rationalizing, but for this story, it's better to work integrally, and then T0 isn't exactly rationalizing, it's just inverting P. So okay, so sorry, let's go back to it. We take an ordinary commutative ring. The L1 is built by combining inverting P, which is exactly what we see here, and inverting V1 mod P. But since R is concentrated in degree 0, when we invert V1, we get 0, just for degree reasons. When you look at the colimit, you're eventually hitting 0 no matter where you start. So for an ordinary commutative ring, L1F, L1FR is just R1 over P. So that you recover this result here.
You're missing a K.
K? Oh yeah, you're right. Thanks. Yeah. Oop. Stick that little K in there. Okay.
Also, in the classical result, you didn't invert like primes, outside P. Like in the last lecture, I got the impression that when you take T1 or something, like first invert all the primes.
Yeah, I was working in the P local world. That's right.
There, like, you don't.
Here I don't, no, yeah. So here I'm working integrally, and I take this convention, which is the convention of this purity paper.
So now forgot, where you define L, maybe L n plus 1 F is the...
It was, well, never mind how I defined it. It was defined by a universal property, but you get it by gluing together all the LTIs where I ranges from 0 to n plus 1.
So you literally take product.
Excuse me?
You literally take product.
No. You glue them together along. So sometimes when you apply one of these and apply the other, it's a new object. It doesn't reduce to one of them, and then you kind of amalgamate. Yeah. In kind of but it's just an inductive way. It's not like you have to. There's no complicated diagrams you have to write down. It's just. Okay. And then this is kind of redshift part 1. So this is Clausen, Matthew, Naumann, Noel. If LTN of R equals 0, then LTN plus 1 of the K-theory of R is equal to 0. Here R should be commutative. Oh, that was 2.
By the way, for rings, I think that Thomason, various people consider as a negative K-theory. Here you ignore it or not.
That's a very good point, Ofer. Thank you. I'm mostly ignoring it. And the reason is that I'm mostly going to be applying Tn localization with n bigger than or equal to 1. Yes. And that, so yeah, let me actually make this remark. If So the Tn localization, again, because it's enforcing this periodicity, it's only ever grabbing things from really high up. So to calculate the Tn localization, you really only need a high enough Whitehead cover. So the Tn localization of a spectrum and any kind of thing where you chop off at an arbitrary point and replace by 0, you're going to get the same answer. Because the V1 is always reaching way higher and higher and higher up into the Whitehead tower.
So is it true that Ln plus 1 f of x is the same as Ln plus 1 of...
No, but only because of this guy. So for n equals 0, it's not quite like that. Yeah. But for this reason, but note that I'm applying. We were talking about the K theory on the outside. So for on the level of K theory, it doesn't matter whether you take connective or non-connective once you're hitting it with one of these guys. That's the. Okay. Right. So higher chromatic generalization 3. So this would be descent. So if say A to B is so if G is a finite group, A to B is a G-Galois extension. So let's say P V1 Vn minus 1 complete G-Galois extension of Tn local rings, commutative rings, then Ltn plus 1 at the next height, you get the descent property.
Covalent ring, covalent ring spectra.
Yes, yes, yes. Yeah. So this is right. So this redshift part 1 is supposed to be a generalization of Mitchell's theorem that we had earlier. Descent was supposed to be a generalization of this very soft form of Thomason's theorem that we had earlier. And let me make a remark. So in general, so the redshift philosophy of Rognes, Ausoni-Rognes. It was more than a philosophy. I mean, they proved results that pointed in this direction, but maybe I'll get to that later. Says that algebraic K-theory increases chromatic complexity. So that's kind of what's happening here. If your chromaticness of R stops at n, then your chromaticness of K of R stops at n plus 1. And then in general, just like with Thomason's theorem, you're supposed to have good properties at the very next height. So this descent theorem is an indication of that when you work at the next height, you get nice properties for your Tn local K theory. And let me also remark that the converse to redshift part 1 holds, i.e., so if you have if you do indeed have non-trivial chromatic information at height n in R, then you have non-trivial chromatic information at height n plus 1 in K of R. That's a result of Yuan and Burklund-Schlank. Yuan. All right, let me make one final remark. So 2, meaning redshift part 1, implies that if you take the n plus 2 local K theory of the LNF local sphere, you get 0. And if you combine with purity, we get a strengthening of purity. You don't actually have to include too much of the lower chromatic information. It's enough to just remember the chromatic information at n plus 1 and at n and glue those together. You don't have to worry about all the stuff that happened before. So for n bigger than or equal to 1.
Do we need a commutativity for that?
No. Because, I mean, you just use that. I mean, this is a ring, and if it acts on some, I mean, yeah, you don't. OK. C'est bon? Yeah, OK. Yeah. All right. OK. Let me say that what the ansatz is going to be for. So I want to give some proofs. I realize I'm kind of running out of time, but so the ansatz for this class will be we will prove statements in the simplest case, which exhibits the relevant features. So I'm not going to try to explain proofs like of the theorems that I'll be discussing. I'll just pick one special case such that the proof of the special case will kind of illustrate what's going on in general. And in this case, we'll prove just the classical analogs. So what I mean is the situation where R is an ordinary commutative ring. For these things which I called higher chromatic generalizations. Okay. Maybe I'll keep the statements out. Well, no, let me not. Okay, so let's say purity. So if R is an ordinary ring, so let me give the proof sketch at least. So how do you prove something like this? So the first step is to use a localization sequence. And here it's good to, well, you kind of have to pass to the perfect complex world in order to get a completely generally valid localization sequence. And what you get is that k of r 1 over p, you can identify the fiber of this map also as the k-theory of something. And it's so it's the category, I'll call it perf R on P. It's just the perfect complexes which are supported at the set theoretically on the locus where P equals 0. Or in other words, it's the perfect complexes that die when you invert P.
Yeah, but here there is a small problem of extending vector balance from R of 1 over P to R. So when you do it with negative groups, it's also...
Yes, but as I already explained, we don't have to worry about this. So there will be, I'm doing a proof sketch, and there will be such bookkeeping details will be completely neglected for in the interest of time. Yeah, but you're right. So it's enough to prove that the T1 local K-theory of this guy vanishes. But then there's a small lemma, a lemma, which says that we can write this category as a colimit of categories. So every perfect complex which dies when you invert P actually admits the structure of a module over this ring. And that structure is essentially unique. If you increase n, so the transition maps here are the forgetful functors. If you increase n, kind of the lack of uniqueness goes away. Now, this category here is linear over z mod p to the nz. So its K-theory is a K-theory of z mod p to the nz module. And then K-theory also commutes with filtered colimits, so it's enough to show that that the T1 local K-theory of z mod p to the nz equals 0. So this you use induction on n. Starting from fact that if you work at the prime p, then this is just, this sits in degree 0, which is a result of Quillen. So that means that, again, because it's bounded in range, then the T1 localization will vanish. So now there's a very nice trick which comes from Lahn-Thoma excision. So we want to show that, basically we want to show that, so we can want to show more generally that LT1K sends nilpotent thickenings. Let's say of Z algebras to isomorphisms. We're actually interested in this only a priori for things which live in degree 0, but let me make the claim for more generally for connective Z algebras. So trick coming from Lahn-Thoma excision, it's enough to show there exists some capital N such that LT1 K theory of A is always the same as LT1 K theory of tau less than or equal to N of A. So this is a little bit strange when you first see it. So if you have this very weak version of being able to, you can think of the higher, for these purposes, you think of higher homotopy groups as always being nilpotent. So part of being nil invariant should be that the value on A will only depend on, will be the same as the value on like pi 0 of A.
Is A connective?
Yes, A is connective.
And
Connective and let's say Z linear. But there's a beautiful trick which I don't have time to get into based on this really powerful version of excision that Lahn-Thoma proved, which says that it's actually once you get to any finite truncation, then you automatically get all the way down to 0, and then you even get nilpotent thickenings for free. I wish I had time to explain it because it's beautiful, but I don't.
But so you realize kind of shifts, sorry, like lower truncations and fiber products or...
Yes, exactly. So in the first step, say you want to get from Z mod P to Z mod P squared, you'd write Z mod P squared as a fiber product with Z mod P, and then Z mod P direct something sitting in degree 1. And then you have this circle dot construction. And in the best of all worlds, that would be a fiber square also after K theory, and then you could make the argument. But that's not exactly how it works. But anyway, yeah. Now, what are we going to choose N? So we choose N approximately equal to the lowest dimension where V1 exists unstably. So recall that V1 was this map from some suspension of S mod P to S mod P, but because it's a map between finite spectra, it has to come from some map between finite spaces. So there's some Sn mod P, some suspension of Sn mod P mapping to Sn mod P. And then we have some unstable V1, which gives rise to this. And that's basically going to be our capital N, the capital N that we choose here. Okay. Now, K theory. So again, we can also neglect. So now we're going to use the vect perspective on K-theory instead of the perf perspective. But we can actually neglect non-free finitely generated projective modules. Because again, that only affects K0, and we're applying this periodic localization functor, so it's only going to grab high enough homotopy groups anyway. So, so then, K-theory of A is built from, as a spectrum, things like sphere BGLNA. There's functorially. And this is built from in the sense of colimits and smash products. Basically from the definition of group completion. Definition is group completion. Maybe need to do a bit more work, but it's fine. So it's enough to show that LTN S BGLN A maps isomorphically to LTN S BGLN. Oh, it's a different N. Excuse me. DA. So tau less than or equal to capital N A. Now for this, as kind of my choice of n potentially already indicated, we use some unstable V1 homotopy theory. So the existence of an unstable V1 means that you can define like V1 periodic homotopy groups also of a pointed space, not just a spectrum. And then there's the lemma of these guys, but it's actually basically the hard work is a result of Bauss field. If f from x to y is an n-connective map of pointed anima, which is an iso on V1 periodic homotopy, then and let's say and is torsion, and xq, yq are contractible. Then LT1 sphere x, LT1 sphere y is an isomorphism. Let me, for safety, C mod p to the nz algebras. Yeah. Okay, so right. So by this lemma, we only need to show that on V1 periodic homotopy, there's no difference between this guy and this guy. Now this guy is truncated, so clearly there's no, the V1 periodic homotopy here is 0. So we need to know the same for this. But this, in high enough degrees, I mean, once you get rid of pi 0 and maybe pi 1, once you take enough loop spaces as a pointed space, it'll be the same thing as this, which is just a product of copies of A. And since A came from an HZ algebra, it also has no V1 periodic homotopy for the same reason as before, that V1 will kill anything, will kill HZ. Okay. Well, I wanted to present some proofs, so I did it. Any questions about that?
You relate BGLD to M. You say that this on the left side, BGLD.
Yeah. Oh, yeah. So if you take a loops, yeah. So if you take a loops on BGLDA, that's GLDA, which is actually just a subset or subanima, a union of components in matrices, which is a to the n squared. So then if you loop again, you actually, then the pi 0 information goes away, and you get that this is the same thing as like loops 2 of an squared. So the V1 periodic homotopy will be the same.
Okay, so A is what? A is a...
A is a ring, connective ring spectrum.
Connective ring spectrum over the Z, over Z.
Over Z, yeah. I mean, that part is not relevant for this part of the argument, but for then concluding that there's no V1 periodic homotopy, then it becomes relevant.
Okay.
So there's so implicit in this part of the proof is a remarkable set of facts about V1 periodic homotopy, which is best encapsulated in something called the Bausfield-Kuhn functor, which, well, I think I'm going to have to stop. I'll have to revisit it. But the basic fact is that the V1 periodic homotopy of a spectrum actually only depends on the underlying pointed space. So somehow you can exchange different spectrum structures on the same thing, and the V1 periodic homotopy doesn't care. So you can go from like a multiplicative thing like GLD to an additive thing like matrices, and the V1 periodic homotopy doesn't change.
Okay, although it is not defined because you are working in spectra, so it's not defined on spaces.
Yeah, but it turns out that it secretly is. So that's the story of the Bausfield-Kuhn functor, which I think I will discuss at some point, but right now I've run out of time, so yeah. Any questions?
Yes. So do higher VI maps lead to some maps of spaces?
Yes, any map between finite finite spectra lifts to spaces. Yeah, there's some Freudenthal suspension. Yeah, yeah. Or maybe that's by something or another. I guess you don't even need Freudenthal suspension. No, it's just by some compact generation argument. Yeah, yeah.
But the V's are not. So when you start with a finite spectrum, so coming from a finite Seedup suspension, everything that you do, like P and VI, is okay. Everything will be a finite spectrum.
Yeah.
Okay.
Yeah.
So morally, K-field is very nice because somehow it's glued out of BG.
Yeah, at some point you have to use the definition of K-theory. Here's one point where you use the definition. Yeah. Okay, so let's call it quits for today. See you on Tuesday.